This episode is brought to you by my friends at Patreon. If you'd like to join them and get early audios of upcoming episodes, please see the link in the description. And, once again, by Singularity G3, now in his 4th year as my illustrator. Let's call it 2.5 out of 3. I have this thing called the exoplanet Triple Crown. It's something I bring up nearly every year, and every year wonder why it hasn't been found yet. A planet wins the exoplanet Triple Crown if it 1. Is Earth-sized, 2. Has water, and 3. Is in its star's habitable zone. It is remarkable how many different combinations of 2 of these criteria we have found so far. Water and habitable zone? Check. Earth-sized and water? Check. Earth-sized and habitable zone? Check. Either nature is toying with us, or the rare earth proponents have a point. I have said often that should a planet win the Triple Crown, it would automatically be my discovery of the year. As you can probably guess, LHS 1140b, planet orbiting a mid-sized red dwarf 49 light-years away in the constellation Cetus, did not. But it came darn close. It is a super-Earth about 5.6 times the mass and 1.7 times the diameter of our own planet, and lies at a distance to its star less than a tenth Earth's from the Sun. Its star, LHS 1140, like all red dwarfs, is much cooler than our Sun, so its planets must huddle close to its hearth for warmth. At that distance, according to Indiana University's planet temperature calculator, LHS 1140b would possess a surface temperature very close to our own world, provided its greenhouse effect was 3 times stronger. 1140b's distance also very likely means it is tide-locked, with one face permanently facing its star and the other in permanent night. So, what's the problem? Well, it's big. A planet with nearly 6 times Earth's mass lies in a gray zone between Earth and ice giants like Uranus and Neptune, which are about 15 times Earth mass. For years, astronomers wondered if 1140b was a super-Earth, a primarily rocky planet, or a mini-Neptune, one composed primarily of gas or superheated liquid. Well, in July this year, James Webb gave us the answer. After snapping a shot of 1140b's atmosphere as it transited its star, Webb found no traces of hydrogen or helium, which one would expect to find in the upper atmospheres of even the smallest ice giants. 1140b was indeed a super-Earth. More excitingly still, Webb also detected the presence of nitrogen. Given that the boiling point of nitrogen is minus 196 Celsius, that nitrogen is almost certainly gas, meaning that 1140b has an atmosphere, and one very much like our own. Except, given that its short orbital period, 25 days, gives us its radial velocity, and thus its mass, we also know its density, and that density is almost equal to Earth, despite its far greater volume. That means that a sizable portion of its mass, up to 20%, must be composed of water. 1,000 times the ratio of Earth. 1140b isn't a fantastical water world with reefs and undersea mountains just out of view. It is an azure abyss with water stretching thousands of miles into the depths. Assuming, of course, that it isn't frozen solid. Everything depends on the amount of CO2 in the atmosphere. It might be an ice world, like Jupiter's moon Europa, or an eyeball planet, a hypothetical tide-locked planet that is completely frozen, save for one circular patch at the point just below the Sun's permanent midday position. The team conducting the study calculates such an ocean would be 4,000 kilometers wide, or about the area of the North Atlantic. EHS 1140 is about the same age, or older, than our Sun, and is also far more stable than usual for red dwarfs, making it easier to spot transits, but also, potentially, easier for any nascent life. it's difficult to imagine what forms that life could take in that unfathomable, featureless dark. That won't stop me from trying. New Horizons blows dust at NASA. Even before the Musk-induced conflagration of 2025, NASA's New Horizons mission to Pluto and the Kuiper Belt was already on the chopping block. Despite superb scientific returns on both Pluto and the farther KBO Arrokoth, administrators were slowly bleeding patience over the team's to-date inability to locate a third destination for the craft. That's not to say the team have not found any potential destinations. They have. Dozens, in fact. But none, so far, along New Horizons' trajectory, or within the reach of its fuel cells. But just when NASA was about to place the craft in low-power mode with the Voyagers, New Horizons defiantly showed that it was out there for a reason. One of the more endearing instruments in the New Horizons array is the Venetia Burney Student Dust Counter. Named for the 11-year-old girl who named Pluto, it is the first interplanetary instrument designed entirely by students. Grad students, don't think erector sets. It's essentially a sheet of polyvinyl that triggers an electric charge whenever struck by a mote of cosmic dust. And in February, a team headed by Alex Donner of the Laboratory for Atmospheric Space Physics at the University of Colorado Boulder, the same university, incidentally, whose students built the counter, found that at 60 AU from the Sun, double the distance of Neptune, the solar system was kicking up much more dust than models predicted. Dust is produced through collisions between asteroids, and over the course of 3 years, during which New Horizons traveled from 45 to 55 AU, the dust counter saw little appreciable decrease, despite observations suggesting a massive sudden drop-off in the number of Kuiper Belt objects after 50 AU. The fabled Kuiper Cliff. And that's not all. As New Horizons trawls through the outer solar system, ground support is offered by the Subaru Telescope, Japan's outpost at Mauna Kea in Hawaii, which has trained its eye in front of New Horizons, looking for potential oases. Over the course of the last few years, the New Horizons team found 240 such objects, while an independent Japanese team, re-examining the data, found 7 more. While none are on New Horizons' route, 2 of these new objects startled astronomers by being beyond the 50 AU limit for the belt. All this suggests that the Kuiper Belt, much like many circumstellar disks observed around other stars, might be as much as double the width originally thought. There may be a gap between the observed inner belt and a hypothetical outer belt, which raises the question of what is causing it. All praise to plucky New Horizons, who reminded us this year that it is an uncharted territory, where even the smallest discoveries can upend our place in the universe. Long may its cells hum. Does dark matter? I've always been suspicious of dark matter. Despite people who have spent their entire lives engaging with the universe at a far deeper level than I ever will, insisting on its existence, I've never been able to shake the idea that being a substance that, as far as anyone could tell, did exactly one thing and nothing else, made dark matter essentially indistinguishable from a force of nature. Much like phlogiston or luminiferous ether, it was, I thought, a stopgap until our knowledge of the universe improved. But I'm happy to say I might be wrong, because it turns out dark matter might actually do something else. Dark matter may be matter after all. Who knew? In September 2024, a Spanish-led team published the results of a survey of a number of ultra-faint dwarf galaxies with the Hubble Space Telescope. These galaxies were all within the Milky Way subgroup, either satellites of the Milky Way or the Large Magellanic Cloud. They were specifically selected for their anomalously low star count, suggesting that they were predominated by dark matter. If, as simulations insisted, dark matter interacted with regular matter through gravity alone, then the stars in these dwarf galaxies would condense toward the center and diffuse toward the edges. If other interactions were involved, then the star's distribution would be more uniform. When observations were compared to the models, the former won out, if only by a little. If there is some form of interaction between dark matter and regular matter that doesn't involve gravity, that could be the silver bullet for finally tracking it down. It might even suggest a use for the stuff beyond driving astronomers insane for 100 years. Who set the stage? Was there a moment, a hum of expectation, when the first light shone on the darkened boards? If natural history is a drama, then the first act began with 3 lights. The first one, the Big Bang, is known to everyone. The second, photon decoupling, occurred 370,000 years later, when photons, the substance of light, were free to leave atoms for the first time. After that, for 100 million years, the universe, at least as we could see it, was utterly dark. And then, point by point, the third light flowed into the universe as the first stars ignited and set the hydrogen universe aglow, a time known as reionization. Current theory suggests that the period of reionization lasted from 400 million to 1 billion years after the Big Bang. Yet since it saw first light, James Webb has continuously exploded preconception by finding early galaxies in greater numbers than ever before, whose added energy should have ended reionization 350 to 450 million years earlier. This is in conflict with observations of the cosmic microwave background and the so-called Lyman alpha forest, the clouds of interstellar hydrogen energized by light from stars, both of which argue for a later date. One possible solution is that, after being ionized, hydrogen atoms calm down and regain their lost electrons, requiring them to be lost again, thus delaying the end of reionization. Globular clusters have been observed already replete with dying stars, when the universe was just 700 million years old. In 2024, NASA announced that James Webb had discovered a galaxy at redshift 14.32, less than 300 million years after the Big Bang. To date, the farthest celestial object ever found. The galaxy's luminosity suggested it was already several hundred million solar masses in size, and spectroscopy suggests it already contains oxygen, the product of the deaths of earlier stars. In November, a Geneva-led team identified what they called red monsters, massively redshifted galaxies already the size of our own Milky Way when the universe was less than 1 billion years old. The sheer number of these early galaxies might be explained by the greater density of the early universe, which limited stars' ability to expel matter, and thus made formation more rapid. Another unexpected sign of precocity in our universe was noted in June by a team at the University of Missouri, who observed galaxies already formed into spirals at distances corresponding to 2 billion years after the formation of the universe, 5 billion years sooner than previously thought. Traditionally, spiral galaxies are supposed to form only after eons of collisions and mergers, but if spirals are extant that far back in time, other factors, as yet unknown, must play a role. Stars are not the only early arrivals to the play. James Webb has detected many black holes farther than redshift 4, when the universe was less than 1 billion years old. EGSI 8P7, a galaxy present just 570 million years after the Big Bang, had a supermassive black hole 9 million times the mass of the Sun. UHZ1, a galaxy present just 479 million years after the universe formed, possessed a supermassive black hole, Sears 1019, of 40 million solar masses, 10 times the mass of our own supermassive black hole. Many of these supermassive black holes were not only overlarge, but tens or hundreds of times larger than their comparatively tiny host galaxies should allow. One possible solution to this is that overmassive black holes quench star formation in their galaxies. As these galaxies merge, they grow, and eventually the mass ratio between black hole and the overall galaxies falls into more modern lines, allowing star formation. In December, a Cambridge-led team employing James Webb located a black hole at just 800 million years after the Big Bang. Despite its relative youth, it was already 400 million solar masses, 100 times the mass of our own galaxy's supermassive black hole, and about 40% the mass of its own galaxy, compared with 0.1% for ours. According to current models, black holes can only grow at a certain speed. Push too much matter into a black hole, and the outward pressure caused by the friction of the accretion disk stops any new matter from falling in. But other models suggest the limit can be occasionally sidestepped. If a black hole has a jet erupting from one of its poles, that jet can act like a vacuum cleaner that sucks material into the black hole. In November, a team employing both the James Webb and Chandra telescopes detected a stellar mass black hole apparently consuming matter at 40 times the established limit, reinforcing the hypothesis of rapid accretion. That is the conclusion, or one of them, reached by a multinational team in December, as they identified J0410/0139, a blazar, a quasar with its monster jet pointed straight at us, at redshift 7, when the universe was just 750 million years old, farther than any blazar ever found. Such a monster would have to be sustained by a black hole of 700 million solar masses. For it to exist so early in the universe, 10 times as many similarly powerful objects must also exist at that range, with their jets pointing away from us. This flies in the face of decades of study of blazars, which suggested none of such power could have existed so early. It is possible that the blazar's rage may be an illusion, a product of gravitational lensing, but this is unknown at present. Another possibility is that black holes are born big. I'm not a big proponent of primordial black holes that form from direct collapse like stars during the brief time when pressures and temperatures in the universe allowed for them. True, they are very likely to exist, but using them to solve any lingering mystery when we haven't found any yet is jumping the gun. Still, Francesco Zipparo and colleagues, after observing J1120 plus 0641, the most distant quasar ever seen, argue that they have ruled out any other option. Zipparo argues that these seeds need not be common. As long as they feed and grow, they need comprise just 0.1% of all the mass in the universe. He also asserts that they can be detected. Any mergers between primordial black holes are expected to flood the universe with gravitational waves, which the next generation of gravitational wave observatories should see. Some argue that the excess mass seen in these galaxies is an illusion brought on by the extreme luminosity of the active black holes at their cores. But that still does not account for their overwhelming numbers, roughly double, that James Webb has so far observed. Something set the stage for our arrival. What it was, we do not know. Far-seen change, Desi, and time. The best works are always unsung. The show wasn't called I Love Ricky, after all. And much like its namesake, Desi, the dark energy spectroscopic instrument, has quietly revolutionized our view of the world without anyone paying attention. This year, the project released the most detailed, accurate, and comprehensive map of our universe to date. The glittering web of galaxies expanding into the unknown since the dawn of time. Galaxies are not uniformly distributed. They form complex bubble-like lattices that in 2 dimensions resemble a spider's web. Hence its common name, the cosmic web. It is generally accepted that these bubbles formed as shock waves in the early universe that rolled outward like pond ripples before the expansion of the universe froze them in place. By employing co-moving coordinates based on the assumed expansion rate of the universe, and then checking them with actual distances obtained via redshift, it is possible to measure the expansion rate of the universe over time against expectations. And that's what Desi, an adaptive optical spectroscope attached to the Mayel telescope at Kitt Peak in Arizona, spent 3 years doing, until April 2024, when the first results were published. And physics has not just reeled from these results, it has blacked out and woken up in some very odd places. The DESI survey, a successor to the more famous Sloan Digital Sky Survey, is the most accurate pan-galactic astrometric study ever conducted, the first to attain precision below 1%. This allows a vision of the universe not only in space, but also across time, observing how the universe's expansion evolved from the beginning. When galaxies fall beyond DESI's light threshold, the team turned to quasars, raging accretion disks of supermassive black holes in the early universe that backlight the clouds of hydrogen between the universe's dawn and ourselves, allowing the team to map their density. In its entirety, the DESI survey covers 6 million galaxies and reaches back 11 billion years. Its precision over that extent averages about 0.5%, though it falls somewhat beyond 8 billion years to 0.8%. The precision allows astronomers to map the expansion of the universe onto time and observe whether it has remained constant. One of the earliest findings of the DESI survey, announced in September 2024, was that the universe was apparently clumpier than predicted. Another, released a month later, had far grander implications, as it suggested that the rate of the universe's accelerating expansion may not in fact be constant, but varies with time. It was this finding that a team led by Kevin Croker of the University of Hawaii proposed supported a hypothesis that most people would probably assume was conceived in the land of Oz. The black holes are the source of dark energy. Okay, this will take some unpacking. In 1998, an astronomer named Adam Rees came to the seemingly inarguable conclusion that the universe, which had been known to be expanding for nearly a century, was not in fact merely expanding. Its expansion was accelerating. This made no sense. The universe was literally it. Everything. Acceleration requires energy. But if the universe's expansion was accelerating, where was that energy coming from? To account for the universe's acceleration, so-called dark energy would have to comprise 72% of the substance of the universe. So where was it? In 1981, a cosmologist named Alan Guth attempted to explain why magnets have 2 poles instead of 1, and in the process accounted for another mystery known as the horizon problem. The cosmic microwave background, the afterglow of the Big Bang, is nearly entirely featureless. Changes in its temperature across the entire span of the observable universe amount to fractions of a degree. Why this should be, when over the course of 13.8 billion years, the expansion of the universe should have magnified even the tiniest imperfections into cosmos-defiling boils, is inexplicable. Guth's proposal was that, for 10 to the negative 36 seconds after the Big Bang, a time so short that compared to it, a second would be equivalent to an age of the universe in which every second was also an age of the universe expanded by a factor of 10 to the 50. If, when it did so, it reached the size of our visible universe, then it would have begun smaller than a neutrino. The hypothesis at hand argues that dark energy is, in essence, a replay of inflation. Every time a black hole forms, it condenses matter to a state identical to that at the Big Bang. Rather than a singularity, in this hypothesis, the core of a black hole is a thrumming hive of vacuum energy, which, according to quantum mechanics, can create a negative pressure on the space around it. The more black holes form, the more vacuum energy pushes on the universe, creating dark energy. I must admit, to me, black holes creating dark energy was at first as loony an idea as mountains creating gravity, but it seems at least marginally supported by DESI's findings. DESI has shown that the varying amount of dark energy with time matches, at least to 1 sigma certainty, the creation of black holes in the universe. As more stars die and become black holes, dark energy appears to increase. Cosmology is weird. A completely different conclusion was reached in December 2024 by a team of scientists at the University of Canterbury in Christchurch, New Zealand. One I have to say is far more in line with my own sensibilities. I don't get to chat with scientists very often, but on a rare occasion in which I did, I asked how much money he would place on dark matter and dark energy not existing at all. For dark matter, he grudgingly acknowledged that it was likely to exist, given the multiple independent lines of evidence supporting it. When it came to dark energy, all they could do was laugh. Dark energy makes no sense. It never did. Even attempts to locate its origin seem fantastical. There is an alternative to dark energy, however, that is not only simple but strikingly elegant. As noted, the structure of the cosmos is not homogeneous, but arranged in vast bubbles of galaxies surrounding voids millions of light years across. Einstein proved that gravity warps space-time, but this glib statement fails to truly convey its implications. Time is not absolute. There are regions of the universe in which years are passing as seconds, simply due to what lies near them. Conversely, within such vast voids, absent the pull of any gravity, time flows more freely, 35% more, than it does in our lumpen gravity-ridden galaxy. And so, over the course of the universe's evolution, seconds accumulate into additional billions of years. Added time means added expansion. Added expansion means larger voids, and thus more time. This so-called timescape model is not new, but has been given new life by the DESI findings that dark energy may not be constant. A non-constant dark energy suggests a non-uniform dark energy, which better fits a timescape universe. Finally, we could not explore dark energy without dragging in our old friend, the Hubble tension. The Hubble tension, which I outlined in one of my earlier Best of the Year lists, is the discrepancy between the measurements of the later universe using telescopes like Hubble and Webb and the mapping of the cosmic microwave background by telescopes like Planck. In short, both give significantly different values for the Hubble constant, the rate at which the universe is expanding, with the earlier measurements being about 5 kilometers per second per megaparsec faster than the latter. Despite its name, the Hubble tension ceased to be a mere tension, a problem with an obvious solution, years ago and became a full-on crisis, a problem requiring a complete rethink of our understanding of the universe. Hence its seldom spoken true name, the crisis in cosmology. Crisis was the term used by Daniel Skolnick, the head of a new investigation into the Hubble constant using DESI data, when he unveiled the results in January 2025. What he found was that DESI had created the perfect distance ladder, provided that one could fix the distance to the nearest galaxy clusters. One of the closest is the Coma cluster, which lies a little under 100 megaparsecs from Earth. At least, that's the accepted value. Skolnick and co. determined to fix it properly, employing standard candles, like Type 1a supernovae, which always explode at the same brightness and so provide accurate distances, and Cepheid variables. The final distance to the Coma cluster, as measured by Skolnick and his team, was 98.5 plus or minus 2.2 megaparsecs, a number in alarming accordance with previous measurements, suggesting that, once again, values for the younger universe are out of sync with those of the older. More and more, says Skolnick, the evidence is piling up that our understanding of the universe is flawed, and that a fundamental reevaluation is required of our most basic models. The fault, then, is not in our stars, but in ourselves. There is hope on the horizon. Rees argues that the infrastructure required to resolve the crisis in cosmology is already in place, and that the next generation of telescopes, once shown first light, will reveal the answer. Thank you, fellow seekers, for getting through what will almost certainly be my last end-of-the-year video. I'm not entirely sure why, but these videos are getting harder and harder to make. I don't know if that says something about me or about the current state of science. In future, I will almost certainly confine myself to posting short videos on the topic of news, both for my audience and for my mental health. I do believe my next big video will be less of a drain on our patience, both yours and mine. Please like, comment, subscribe, etc. And I hope to see you in my next project.